thank you. Let me know if you can't hear or if you're not. If I'm drawing in a place where you can't see. So what I talked about today is the idea of structures onto barcodes. So, and I'm talking about structures here. I could be talking about metrics, for example, systems. But what I'm going to be talking about mostly today is a more algebraic geometric structure, which is like coordinates on the set of all barcodes. So why I want to do that first? Why I think that's an important thing to do. So one reason is that so why important? It would be databases with geometric, for example. So it might be compounds. One could study the level sets of the intensity function and get geometric objects out there to which you would then attach barcode. In addition, these databases are hard to deal with, and so you'd like some kind of organizing principle for them. And a structure on a set of barcodes allows you to get a structure on this database and to get a better handle on it. In coordinates, if you coordinatize it, you can treat this kind of data unstructured data as structured data because you can build coordinates for it and create then Excel tables or whatever. Secondly, though, and this is where I'm going to talk about at the very end, which I think is pretty interesting, is doing something useful with multidimensional persistence. So about is that multidimensional persistence, one-dimensional persistence, doesn't really have a good notion of barcode attached to it. In fact, what we found is that the actual classification of the module depends on the field of coefficients that you take. So the object that classifies will be different if I have the complex numbers instead of the rationals. Now, something which is in that way with the coefficients, you want to study that. That's a information that probably is irrelevant, at least at an initial cut. And we know that the classification is essentially difficult. It's like a moduli space classification than sort of a discrete classification. The idea here is that if we get coordinates on spaces of barcodes, we can use analogous coordinates for multidimensional persistence, and where I want to get to at the end today. So let's talk then about like B for the set of all barcodes. Now, I want, it's not just a set of barcodes, it's instruction that I'm going to show you here. So the fact that B and is barcodes with bars. And then, so this will be a collection of intervals, x1, xy2, and where's the ordering? So it's the collection of sets of these intervals. I will, always it'll be the case that xi is less than or equal to yi, but I might be equal to yi. Considering intervals of length 0. Now, of course, what we want to do is we want to ignore intervals of length 0. And here's a description then of the study of barcodes as I want to study today. I want to create functions on this. So here will be the disjoint union of Mullins relation. And is simply the one that's generated by the relation that says, well, if I have x1, y1, yn, and the final one here, which is n plus 1 and n plus 1, I get set that equal to x1, other words, if I have an interval of length 0, I want to drop it or add intervals of length 0 arbitrarily. And that is the set that I want to think of as B infinity, if you like. We'll just call it B. So this is the set of barcodes. And let me just write it, because of the fact that I'm ordering on here. This is what these things really are. If I let I, and I'm getting low here, so let's. So intervals. So x, y, so that x is less than or equals y. Now, I can talk about the n-symmetric product of I equal to I cross I with the symmetric group action factored out. So I will identify any two of these which get identified when I do a permutation of the coordinates. So this is what we call the n-fold symmetric product of I. In fact, we'll write in general SP of any x is equal to the disjoint union of SP of x. So pre-commutative monoid on x. Now, what I'll do though is if I have a subset in here, and if I have one thing in x, I'm going to think that SP of x and y, which is a disjoint union and SP and the equivalence relation, which says, look, I have x1 through xn, and some element in y, I can identify that with x1. So, relative construction, this really turns out to be the same thing. SP of x mod y, and the point, which is the base point here, where I pull off the y and made a single base point of it. Okay, and to check that this is true is not very hard. And what we see then is that B. So this formalism. So SP I and well delta, where delta in I is diagonal consisting of the length 0 interval. Is the same thing then as SP of I mod delta and this base point. Okay. This is this set for which I'm hoping to create functions. So I want to create functions on this. Okay, let's step back then for a second and let's see here. So I'm going to talk about the notion of varieties over R. So what these are, varieties over R are simply zero sets of equations over R. But it turns out when I have that, those sets of equations that set to 0, the ideal inside the polynomial ring on R, say n variables, if the variety fits in. And so there's something called the affine coordinate ring. So if V is a variety, it's F1 through Fn, then we'll write the affine coordinate ring of V to R of, if these functions here, Li are functions from R, K, polynomial functions. Polynomial. Then x1 through xk, my field generated by f1 through f. And actually, we're going to take its radical. Is that, in fact, there might be elements, so some power of them is in this idea, and they will also then, of course, vanish on saying set V. So this notion right here is an affine coordinate ring. This ring has no nilpotent, so this is a reduced R algebra. And there are no nilpotents. Interesting is the algebraic geometers discovered that there's a very good correspondence between the varieties in these affine coordinate rings. They really determine each other. And then further and said, actually, for any R algebra, you can say so number A, called A. And I won't go through the details of this, but the points are the prime ideals in the ring A. And it turns out that you can then recover the variety just ideals inside A. But of course, A has not come from this kind of algebra. One can still build the space. In fact, there's a notion then of so-called affine schemes. What that means is it's the set of spaces of the form XA together with a ring of functions on it corresponding to A. Varieties are embedded in there, so varieties are contained in here as things coming from the category now that includes the category of varieties. This is called the category of affine schemes. Is isomorphic to the opposite category of the category of commutative R algebras. To bring this up is now the following. So let's remember that, and now let's go and think about how we might create some functions on barcode spaces. Second, let's take B again. The set of n. That is the orbit space. So that I n mod sigma n. I can think of the I sitting inside R2, right? If I just forget the ordering condition that x is less than or equal to y. So this sits inside R2 to the n. Now an orbit space is sigma acting on R2 to the n by permuting these collections of n vectors. Here's the thing. So the question is, R itself is a variety. So, R2 it corresponds to R and Y. R to the n, for x1, y1, all the way up to xn, yn. The question is there a ring that corresponds to this orbit space? And the answer turns out to be that there's a very simple ring that corresponds to it. So the ring corresponds here. Ring of invariant functions. And for a second, it makes total sense because for that invariant function, it's actually defined on the orbit set because it doesn't matter what orbit representative I take. Functions, at least on this on Bn, because I can restrict the functions here to this part. This right here, if I have only x's, something that's very well understood. This is the ring of elementary symmetric functions. The thing I've got over here where it's acting on x's and y's, this is more complicated. It is definitely in the theory R algebra. It's generated by a finite set of generators, but you can't make it freely generated by those. There actually are relations. So there are relations among generators. it's a ring that we work with, and it's a ring that's been studied actually fairly intensively recently, more recently than we think, so the last 10 or 20 years. I don't just want functions on Bn, I want functions on that I call B, which is that relation. So I need functions on B. So it turns out that B of set. So like this, I'm simply going to take it as follows. So I was I, because remember we set it up there so that it's going to be product of I mod delta with identifications coming from being off the base point. So I have this mapping into here, including it by 0. So I will set alpha comma delta and SP3. So I've expressed it as a limit here of spaces or of sets. What that comes to then is it corresponds to a direct limit of these affine schemes associated with these things, although it makes sense that this thing is a scheme. So now that thing makes sense as a scheme. So delta is the push out of the following diagram. So it's delta contains I, and delta goes out to point here. No. So the I mod delta is a push-out diagram. It's a limit of the diagram of these two push-out diagrams. It's a sort of affine R schemes made into, it's a complete and co-complete, so it has all possible co-limits and limits. And so I actually make this thing here where I take, I'll take R1 as the diagonal into 2 out to point becomes scheme. So I want delta. Ring does that correspond to? So it's actually pretty interesting because it corresponds to is the following. So then I take R. So let's draw this. It's going to now be a diagram like this. So we're going to have a polynomial ring X and Y, and I restrict that to the diagonal. And I send X and Y to the same thing. So we'll raise this C. Then over here we now have map Y going in here. X and Y both exceed. I could coordinatize this and make this as RC, where it's X plus Y, and eta, where it's X minus Y. So C equals X plus Y equals X minus Y. So to do that, let me erase the X and Y here. C goes to C in here, but the co-limit turns out to correspond to the inverse limit of this diagram. So, what's the inverse limit pullback of this diagram of rings? Well, what is this? It says that if I have anything that has C in it, it will have something non-zero here, and that thing has to be constant. In other words, the pullback of this ring R of C monos A where A is greater than or equal to 1. In other words, I can't have any CI sitting all by themselves because they're not in the inverse limit. What's interesting about this ring is that it's actually an infinitely generated algebra, so we've kind of left the area of varieties here, but nevertheless it exists as a commutative R algebra. Okay, so the thing that corresponds to this I and mod delta. So I can then make these constructions here because the SP thing and just take the ring of functions, tensor it with itself, and take the sigma n invariance. So I can create each of the steps.
So that j is greater than or equal to I? Or equal
Greater
to
than or
1?
equal to 1. So this algebra, we'll call algebra D. Or what we're going to create, we can then study D itself 10 times. Sigma under sigma n. That'll be the thing that we call that's the ring attached to B R2. And I've expressed them as a direct limit here, the corresponding notion on the inventory of rings. So for rings, we get an inverse system. So the tensor cube, 3, so forth. Then deserves to be called the ring of functions on the space. So this would be called the ring of functions. Unfortunately, there's a problem with it, which is it's written as an inverse limit of rings, and in fact, it's very difficult to describe it. It looks like a subring of a power series ring, but with a lot of complicated conditions on the sums being finite. So let's imagine the analogous situation where I take, R and then R2, 1, 2, R3. The ring, it looks like it contains. So let's just write in an inverse. The ring of symmetric functions contains some infinite sums as well. And you can characterize what it is in this case, but you don't really want to. If you hand these coordinates over to someone who does machine learning, for example, you don't want to have worrying about convergence conditions. And so what we'd like to do is we'd like to characterize somehow this ring of functions here, this one that is just finite polynomials in some intrinsic way. And it turns out that the way you do that is that the group R star, R being the group of non-zero real numbers, and by multiplication, R2. If I'm multiplying both coordinates, it will preserve the diagonal. What we need to do is to actually build the graded ring. So consider the graded. With A is the coordinate ring here, and I've got G acting on it. A, the n-homogeneous part, is all those alpha such that acting on acting on x is equal to the n. And so what I then get, I can get a graded ring. It turns out that in the category of graded rings, the infinite is actually just these polynomials. And so what I'll do is I'll grab the finite function. Well, I'll say finite functions. It will be a ring. Define ring attached to the graded ring. This of k-finite functions comes out of representation theory, where people they're often in this position of having to identify some measurable algebraic functions into some much larger completion. And so now the result, Gunnar Carlsson, myself, and this ring of functions for the barcode space. So for the barcode space, the ring of finite functions is it's a ring in the parameter family of generators, tau ij, where j must be greater than or equal to 1. And here, by two parameters, the degree of tau ij is equal to I plus j, and I'll give you an idea of what some of these functions are. For example, tau 0, 1 corresponds to the sum of yi minus xi, the sum of the intervals. K is equal to the sum. These are like the power symmetric functions. Those. And 1 is the sum of xi plus I minus yi. Like that. The rest of it, general tau A equals, tau KL equal to I of x plus yi k x minus yi to the L. It becomes clear why it is that L has to be greater than or equal to 1. It's because otherwise I would have a sum which might involve only x plus yi, and that would be a function which is not invariant under the process of removing intervals of length 0, because functions can have very large values for intervals even of length 0, because it's like taking the sum instead of the difference of the endpoints. All right, so result, and we actually found that to be useful in some work of Anthony Back, who I think many of you know. Together, Michael Lerner has worked and gotten some very interesting results on classifications of compounds involved in suppression of various cancer processes using exactly these functions on bars coming from the chemical structures. But the thing to get to here at the end is how does this help with multi-D persistence? Have a set of barcodes and so how can you have a set of barcodes? How can I use this? Well, that I can actually real functions in another way. So it can also be thought of as integral. So, for example, to put a barcode, the barcode looks like this. And so I can think of the barcode as a function now, because what I can do is, as I move along the real line, I just count the number of points that sit over that point on the real line in the barcode and get a function. So in this case, I have a function that would look like, over 0, and then, so here's 0, 1, 2, and 3. And so the function looks like this, is 0, and then all of a sudden it goes up to 1, and then 2, and then 2, and then 1. Barcode is being represented by these piecewise constant functions. Interesting fact is that, and it's not very hard to see, is that if I take the integral from minus infinity to plus infinity of code of this function, so call this beta, this is phi beta, tau 0, 1, which is equal to the sum of the lengths. Getting at these functions, which is not some explicit knowledge of the barcodes, it's simply coming from this dimension function here. So consider, for it to create some of the other functions, I might also consider integrals. See, here it's kind of like the dimension function at every point. I could consider integrals involving the rank function over R2 of the rank function. So integrate over R2, and for any pair of points in R2, that are comparable, any pair of points with x less than or equal to y, I actually number to that point, which is the rank of the map from the one to the other. So rho is like of x and x prime is equal to the rank of the transformation, which is dx going to x prime. And that you can find that you can realize all the functions in this one here that we've gotten in terms of certain integrals. It can be realized as integrals. From the algebraic geometry, we don't have to know the barcode explicitly. If we want to do multi-D persistence, let's do that. See, it comes from a barcode and multi-D persistence. So first there is an analog of barcode. So it's sets of line segments, but of squares or rectangles, D cubes, 3D rectangles, etc. And persistence. We've got two variable persistence. Let's just focus on that. Then we have a set of all possible rectangles inside two, and put them together into a barcode space where the idea is now I get to identify. So barcode space. Removing, delete any cube or any rectangle area. So any two, any two of the coordinates for the cube. And by the way, these rectangles are all parallel to the x and y axis. If it's thin, if it's infinite thin, then I get to remove it. It doesn't mean that they're all the same. Just any two pair coordinates being the same. And so it's an analog of sort of barcode space in dimension D. And such barcode will map to a persistence module. Modules come from things coming from barcodes. So I'm now going to tell you about work on So he's worked out what is the ring of functions on this barcode space. So this is not an object now. It's polynomial algebra is bigger. Much like the ones we saw for B. Okay? But having those is not sort of a priori useful unless I can understand the functions that extend to this space of persistence modules. So let's call that top. The question is how can so this ring A, B, elements of the all of them. Also found is that there are corresponding integrals. See here, the rank function takes place in RD cross RD, and the dimension function takes place in RD. Those are the integrals that I can perform. And so what he has observed is that there exists representations of functions. So now we have a rich class of functions that apply to all persistence modules. And we use our intuition that we would get from studying the functions in one variable to this multi-D situation. So we can think of this as the D-dimensional persistence transform. With an object, which is a persistence module, and it is transformed into some understandable ring of functions and some numbers and coordinates. Let me by saying, and I did. So I think this is an extremely interesting thing here. It allows you to, if we can understand the primitive barcodes that it is that we're measuring, if we can get precise on that, then we really start, measuring, understanding multi-persistence. I want to just conclude with the statement of the theorem about the one-dimensional case, and just return to that very quickly. So we have R of these type J's is a the functions on point space into R. There's a rings like this. And the question is, these things deserve to be called the coordinatization of barcode space. And two results that suggest that they are. So the one is they just map J. So J is actually an inclusion. There's no algebraic combination of these tau ij's which advances on all of B. So these are non-redundant and so on. Yeah. And finally, the image of J of R of tau ij. Second point. So if I got any 3 points, there's a function in that algebra which sees the difference between them. Okay, I'm at the end of the hour here, so I'll go ahead and stop and happy to take any questions.
Are there any questions?
Yeah, I have one. Gunnar, a question. So when you look at this multi-barcode, so let's say two-dimensional, space of rectangles.
Yes.
Well, the persistent modules are very complicated, right? So persistent modules that comes from barcodes are actually quite small, part of all persistent modules.
Yeah.
Is it? Contrarily, how much of these functions on the rectangles actually cover the properties of all barcodes? Not barcodes, all persistent modules.
Yeah, that's a great question, and we obviously have no clue on that. But what we're saying is that we have a rich set of functions which sort of are the things that we have an intuition about. And I can step out. Let me continue talking and hold on. Okay, we don't have whiteboard. Yeah, so the thing, oftentimes our intuition about these things, the intuition of barcodes is coming from the cubicle, from this rectangular kind of module. Everything, but what is so urgent is that the functions that we see on there, that we might have some intuition about, actually extend and can be computed on any persistence model.
Oh, okay.
But now it's a great question as to doubt. In fact, I know there are others possible, because this thing in fact tries to depend only on the rank invariant. We have other aspects of it that are more nonlinear, so there's room for developing more functions along these lines. The statement is saying is that there's some intuition that we can use. Yeah.
Sure. So I have actually another question regarding this. when it's, I mean, is there any natural way of defining, for example, two filtration of complexes that would lead, you know, that will allow us that, oh, it's, you know, S homology actually is built from these rectangular barcodes?
You know, that's a good question also. I really have a good sense of that. My sense is actually, it's probably, I think, things that you can build very naturally, you know, will not create, you know, angular objects that create things with maybe a more round boundary.
Right.
So it's hard to say.
Okay. All right. It was great.
Thank you. Okay.
Earlier on,
Okay, you're breaking up.
the bars
You're
being
breaking up.
right by birth and death. The bars as being determined by a birth and death time, with birth coming before death.
Yeah.
So whether this actually matters.
So say that, you know, of course, I'm sort of regarding it as not mattering because I want to take these I want to algebraic geometric functions. But there is something you could do, though, because to include that information. So there's a whole theory of real algebraic geometry which takes ordering into account. So I'm sort of thinking that this begs to be studied in those terms as well, because that gives you, you know, even more precise information. LPD setting.
Gunnar, with these functions, if you take all of them, 1D setting, if you just take if you have a large barcode and you just take some proportion of these functions, then, I mean, to what extent can you reconstruct the barcode from?
Okay, the statement that I just, you know, I showed that this ring was injective and that it separates points, which is supposed to providing a coordinatization. It says that you can, in fact, separates points, says that you can, if it actually comes from a barcode, you can determine what it is. But actually a process which this student Jacek has also developed involving, you know, limits of these functions. It's sort of a complicated scheme, but you actually can reconstruct the barcode. The thing is this, that the base itself, you know, the thing of variety, if you like, one think of it as actually, this also extends to some kind of completion of the, you know, of barcodes. So you imagine a set of barcodes, we're adding smaller and smaller things to it, but it goes on infinitely long. That's something that you can imagine that would be in here. So, but in any case, yes, you can determine them. Yeah, it's complicated.
Hi.
Yeah.
So I'm wondering, if there is a distance on the space of polynomial rings or something which restricts to the barcode distance when you map. Could we define one using this?
Yeah. So I think when you're saying the barcode distance, you're thinking of bottleneck distance.
Right.
So bottleneck distance, the answer is no. This is a bit unstable relative to that. And the thing that might be more stable is there's an actual analogous object that Sarah Koliznik is studying, which is the ring of tropical functions on here. So tropical algebraic geometry is where, you know, you have max taking the role of addition, and where addition takes the role of multiplication. So in there, you know, I think it makes more sense. This is more to be somehow closer to some kind of, you know, P versions of bottleneck distance, that kind of thing. It might be stable there. But if the subject is open to study, I think a way to turn the question around is to say, well, what natural metrics do I get from this coordinatization? Are they new and interesting metrics on the set of barcodes? Okay. Any other? Okay.
So
All right.
maybe go then. So.
Thank you very much. Enjoyed it. Thanks a lot.